Okay, thank you very much to the organizer for putting this session together. So I'm going to talk about some work done with Ultra Guillemin, Tom Bolton, Andrew Ross, Pavel Perez-Hogan, and Alistair Adcroft on the implementation of machine learning parameterization of mesoscale eddies. So mesoscale eddies are turbulent features in the oceans that have horizontal scale of 10 to 100 kilometers roughly, and are pretty important for momentum and tracer transport. They actually set the ocean stratification and its vertical structure. That means that they can impact the amount of heat that is being taken up by the ocean, and that means that they will have an influence on thermostatic sea level rise. So here I'm showing a set of idealized simulation performed by the session convener. And what we're seeing here is the depth integrated kinetic energy at 1/4 of a degree, 1/8 of a degree, 60th of a degree, and 1/32nd of a degree. And so what we can see is the richness of the eddy field as we increase the resolution. So we're better able to actually represent mesoscale eddies as we increase the resolution. Obviously, running climate model, global climate model at those kind of very high resolution where we can resolve the eddy field properly is not going to be in reach for decades to come. So we still need to parameterize that one way or another. Basically, finding a way to represent the influence of mesoscale eddy on the large scale flow without the computational expense of running high resolution simulation. So now let's try to understand which part of the mesoscale eddy process we are focusing on here. And this is the backscatter or the inverse energy cascade. So as resolution decreases, the mesoscale eddies are less resolved, and that also means that we're inhibiting the transfer of kinetic energy from small scale to large scale. And so this is illustrated here when we compute the flux of energy as a function of wave number in the Southern Ocean in a global simulation run at 3 different resolutions. So the thick lines are the kinetic energy transfer. And in green, this is the energy transfer from a high resolution simulation. So we have a negative lobe over here. That means we're extracting energy from the small scale, and a positive lobe here. So we basically have been pushing energy from the small scale into the large scale. As we decrease the resolution, so as the grid box size gets bigger, this energy transfer, this inverse energy cascade is actually reduced. And at 1 degree, it's completely inhibited. That's the blue line. And so this is something that we see pretty much in any simulation that you will pick up. The transfer of kinetic energy from small scale to large scale gets inhibited. And it's the same for the conversion of available potential energy into kinetic energy. And so that's a flaw that you will see in pretty much every simulation that you look at. So here, what we're focusing on is trying to parameterize that inverse energy transfer from small scale to large scale. And so as always, we're trying to parameterize the effect of eddies only as a function of the resolved scale. And this is basically a typical problem of finding a closure or finding a parameterization rule. We need to find a function or a functional form for the effect of the subgrid on the large scale only as a function of the resolved scale of the flow. So the way we've been typically doing it is by trying to come up with a mathematical operator that will mimic the process that we after, or its effect. So there's a suite of nice papers showing how the backscatter can be represented by using negative viscosity constrained by the eddy energy of the flow. And so it's kind of a nice, elegant way trying to re-inject energy at a given scale and letting it affect the large scale flow. So that's the way we typically do parameterization. Write down an empirical physical relationship and basically implement that in a climate model. The more recent approach has been to try to learn from data. I mean, data is the best source of information we could possibly have. So can we actually learn empirically those relationships directly by focusing on the data? And so we've been doing a lot of this work, I guess, using deep learning. So training a deep learning algorithm to actually find features or find relationship based on features that will represent the effect of mesoscale eddies on the large scale flow, trying to mimic this effect of backscatter or energy transfer. Now, the problem with both approaches, right? They're both empirical. With the deep learning, you take a lot of data and you come up with, a bazillion number of parameters, and it's super hard to interpret. With the kind of empirical physical relationship, you're making a huge amount of assumption from the get-go. So here we're trying to find a little bit of a trade-off, or what we call the best of both worlds. I still want to learn from data because this is the best source of information we have, and that's, you know, something we should rely on. But I still want something that I can interpret physically, and so a set of equation, or at least a set of mathematical operator, is a pretty good way forward. So our idea was, well, let's try to discover equations for parameterization from data directly. So that helps with interpretability. And also the huge trade-off is it's easy to implement in a climate model because you already know how to discretize all those operators. And so this is work we started with Tom Bolton back in, a few years ago. Some of the papers have been published, where we give the algorithm, a suite of data set in which we diagnose the missing subgrid forcing, and we ask it to learn an Eddy parameterization by giving it a set of basis functions that are related to the vorticity, divergence, shear, stress of the flow field. And then we extract directly an equation for the effect of the subgrid energy, of the subgrid mesoscale forcing onto the large scale flow. It was pretty successful. We get 70% of the variance. It extract a very nice and symmetric stress tensor without any a priori knowledge. And we were able to actually interpret it based on the earlier work from our group, but from a wide range of other people as well. So we could explain basically how the stretching and shearing of the flow field re-inject energy locally, at least. So now the question is, can we implement that into a model? So as I said, the beauty of those type of discovery from data is it's an equation. So we know what to do with it. So the first thing we've done is we implemented it in a barotropic model, very idealized double gyre type simulation, and compared it to a high resolution one. So down here, this is a high resolution simulation of that barotropic model. It's a double gyre setup, as I said. Latitude up here, longitude over here. We have a jet in the middle and some, recirculations and jets in various places. High standard deviation of the flow field. So that's basically high kinetic energy, a little bit like we saw at the very beginning. At coarser resolution, less variance, the flow is a little bit more viscous and a bit more boring, less structure in it. If we implement the equation discoveries, the parameterization that we discovered directly from data, that is an equation, we can see that we're improving the flow field here. So we're improving the variance. It looks quite similar to the high resolution, even though we're still, at 30 kilometer resolution. So basically 10 times smaller in resolution. And if we look at the structure of the flow is actually weaker, which is interesting. But the structure actually becomes more correlated with the high resolution one. If we compare that with the implementation of a neural net, which had also a physical constraint built in it, we actually reach roughly similar results. Now, again, as I said, the advantage of the equation discovery over the neural net is one, I could understand what it was doing, and it's super easy to implement. The neural net, especially a convolutional neural network, is full of complication when you're trying to do an implementation online. On a simple flow train. In both cases, though, I should mention, the model blew up, so we had to tune it. So even though both parameterization had conservation of momentum and energy built in it, the model was still numerically unstable. So there's still other aspects that we need to consider. So building in, constraint and conservation is actually not enough, as we thought it would be, at least in this case. So if we move on the implementation, it's something a little bit more complicated. So now we went from barotropic, so basically one layer, quite simple 2D turbulence, to a 2D and a 3D actually quasi-geostrophic model. And here I'm showing the flux, the energy flux as a function of wave number. So this is the kinetic energy flux for the parameterization, as I showed you before. So negative, if you remember, we're extracting energy from the small scale, moving it to the large scale. The blue and green are basically traditional low resolution, simulation. And the red curve is a high resolution simulation where the inverse cascade is basically enhanced. The orange line is the low resolution simulation plus our equation discovery parameterization. And here what you can see is that we're enhancing that kinetic energy transfer from small scale to the large scale. So the parameterization extracted from data give us an equation that is actually able to mimic this inverse energy cascade. So we started implementing it in MOM6, so the full GFDL simulation in a very idealized setup, again, of a double gyre. So we're doing a lot of sensitivity to this new parameterization as we're moving forward, and hopefully you'll see some new implementation of convolutional neural network in the way as well. So let me sum up. Mesoscale eddies are key for ocean transport and stratification, and their parameterization will remain on demand for decades. As we increase resolution, I want to make clear that there are different parts of the problem that we're parameterizing. And here it was for backscatter. And in this case, I showed that data-driven and machine learning approaches could help us. So again, here I show the versatility of learning parameterization from data. And there are quite a few examples. Neural nets and equation discoveries are the one we've used, and we should get great success. There are other examples of machine learning subgroup parameterization. So check out Andrew Ross, where he's actually describing metrics across a wide range of ways to actually extract parameterization. And Akash Sen, who's actually looking at the vertical turbulent transport in the ocean with also an implementation into MUM6. So check this out, and there are many others out there. So the advantages of learning equation as opposed to learning, a deep neural network is easily interpretable, explainable, however you want to call that, with the potential for physics discovery, right? You're looking at scale interaction. And so there's new physics that you can actually learn directly from the data. It's highly generalizable, right? And you can go back to basic physics principle. When I look at data, the fact that it will generalize to many things is more likely than when you come up with a very simple empirical relationship. Very flexible for implementation because it's a bunch of derivatives and we know exactly how to discretize them onto the stencils that we have. So I do think it's a very exciting time for mesoscale parameterization for many reasons, right? So first, we have better observations. That means we understand how mesoscale eddies actually interact with the large scale flow that we couldn't do as much before. We also have higher resolution simulation, sometimes idealized, sometimes global, but there are different ways to actually look at that data and understand something about the scale interaction. We have new tools. Machine learning is one of them. But again, there are many out there. And we also have advances in theoretical framework that have happened over the recent years, trying to understand how mesoscale eddy sits in this kind of energy cascade and energy transfer and pathways. So let me close up by saying, check out a lot of other presentations from our climate process team. You can see them over here, March 3rd and 4th. Also, we have an annual meeting that is open to all. So if you work on mesoscale eddies, whether you're looking at observations, you're thinking about theory, you're thinking about model implementation, or looking at high resolution simulation and the way eddies are resolved and impacting the large scale flow and so on, please submit an abstract. It's open until March 1st. It's going to be hybrid, one part in person in Boulder, rest online. So please join us. And thanks again for your attention.